Last time we were talking about universal validities. This is here in section 335. Right? So a universal validity is something that is true in every structure. So these are formulae which are true in any structure. No matter what the assignment is. So we saw that we could express this. I can take any structure. So I'd say a formula phi is universally valid if for any structure I take and for any assignment function of variables of the language to n here. The formula phi under that assignment comes out true in n here. So for any structure at all, for any evaluation, so it doesn't matter where we look, when we interpret the formula phi, it will always be true in any structure or model, so synonym structures and models. So we kind of put all of this to one side. So we write this just to say that phi is a universal validity. Right? We drop the m and the quantifiers and the w and so on here. So it's clearly of interest to find which formulae are universally valid. I mean, there are some obvious examples. If I just say some term equals itself, right, this is something that's going to be universally valid. But there'll be more interesting universal validities than this. And one could ask, is there an algorithm that'll check for us whether a particular formula is a universal validity or not? It's a perfectly reasonable question to ask, and it turns out that the answer is no, there isn't. But there are a wide class of formulae which we can confidently assert are universal validities. And these are things that are instances of tautologies. So let me explain a little bit about tautologies. So basically a tautology is something that's true just by virtue of the structure of how the formula is written out. Since we want a universal validity to be true in all possible structures, same thing is true for tautologies. It's just the structure of the formula itself that makes the thing true. So for example, if I take here, whatever this p might be, P or not P here. We say this is a tautology because it's going to be true whatever we think of P, whether it's true or false, this thing is always going to come out true. And as we've seen in the Foundations and Proof course in the first year, we can assess whether something is a tautology by looking at truth tables. So I'm not going to go into a great formal definition of this, but here would be a truth table for this. Here we write out the possibilities for P, true or false. And here we have P or not P. Well, if P is true, this is false, and this is true here. And now I've got P or not P. So either this or this. Right? So this comes out true, and this here comes out true. So a tautology is, generally speaking, something like this. Right? It's something where I can think of sort of propositional letters, kind of fancily called propositional atoms, right? And I string them along using our vocabulary, our auxiliary vocabulary here. And if I look at a truth table for it, it comes out true here. So and if one has P, if one has two letters here, we look at the truth table for P arrows Q. Here we have true and true. We look at all possible distributions of truth values here. Because there are two letters in our formula, there's 2 to the 2 lines in the truth table. And this is always true except for this case here. And now if you put down next to this, here I look at not P, false, false, true, true. And now if I look at not P or Q, so not P or Q is true here, this is false because neither are true, here this is true, and here this is true. So we see that not P or Q is equivalent to P arrows Q. It has the same distribution of T's and F's on the different lines of the truth table here. So we can deduce then from this that P arrows Q can be expressed using not P or Q. So P arrows Q is not a tautology because there is a line on the table where it comes out false. Right? So P arrows Q is not a tautology. So in general, a tautology is a formula using, let's say, propositional letters So the idea of a proposition is, propositional formula is one kind of without quantifiers. Propositional letters, or sometimes called atoms, I think this is what it says in the notes, maybe it's using propositional letters P1 up to Pn, right? So is a formula, let me give it a name, A. No, let's call it something else. Let's call it big phi. So when we write out the truth table, for phi, we get a T on every line in the final column. So it's going to come out T no matter what distribution of T's and F's, trues and falses, we assign to these propositional atoms here. So this gives us then a class of universal validities in our first order languages. So if we have formulae in some L, let's call them psi 1 up to psi n, we can substitute those formulae in for those propositional letters p1 up to pn, and I'm guaranteed that the resulting formula of L will be true. So we can substitute the psi I for the pi, and here, and we're guaranteed to have a universally valid formula. So we're guaranteed to have a universally valid formula. Irrespective of whether the psi i's individually are true or false, we know that when I put in the psi i's for the pi's, the whole thing will then become true because the formula capital Phi was actually a tautology. So, example. So P1 arrows P2 arrows P1. Okay, simple formula using just propositional atoms, just P1 and P2. If you look at the truth table for this, you'll get T's on each of the 4 lines that this truth table will have, right? Here. And now I pick any formula, let's say psi 1, so, just pick something. For V0, phi 0, psi 2, well, let's say not exists vk phi arrows chi. So I'm just thinking of things at random here, right? But I'll know that psi 1 arrows, psi 2 arrows psi 1 will be universally valid here. The structure is irrelevant. What assignments we make to the free variables in here, completely irrelevant. This will be true because this underlying template, for which this is an instance of this, is a tautology. So a formula like this, we say is an instance of this tautology here. So let's call this A and this B. So formula A from L is an instance of this tautology here. Instance of the tautology B. Here. So what we see is that if you want to write down some universal validities, what one can do is find some tautologies like this here and just do some substitutions in here. So anything that we can check is a tautology, will generate for us, well, infinitely many universal validities here. And there's one point to make, is that checking whether something like this is a tautology or not is a computable procedure. It's quite effective. After all we have to do is just write down a truth table with 4 lines in it. So we can program a machine to do this. So, important point. Checking a phi with propositional atoms for tautologyhood is a computable procedure. Sometimes called an effective procedure. Because all you have to do is write down the truth table. Right. So a large class of universal validities, the ones that are instances of tautologies, are universally valid. On the other hand, it can be shown that there is no computable procedure for testing in general whether a formula of L is a universal validity or not. And this we will be looking at later in the course.